5 water bottles went into the freezer. I froze them completely solid. Then I covered them with salt. And what happened next was not what I expected, because one bottle started changing almost immediately, while another looked completely untouched. But before I show you which one changed the most, we need to start with 5 identical bottles. Same size, same amount of water, same freezer, and the same amount of time. The only thing that will change is what happens after they become solid ice. I'm calling them Bottle 1, Bottle 2, Bottle 3, Bottle 4, and Bottle 5. Bottle 1 will get no salt at all. That's our control. Bottle 2 gets a small amount. Bottle 3 gets more. Bottle 4 gets a heavy layer. And Bottle 5 gets the biggest salt treatment of the entire experiment. The goal is simple. Can salt actually defeat a water bottle that has been frozen completely solid? Because if these bottles are truly frozen, there shouldn't be much left to melt. So I put all 5 into the freezer. And now we wait. At first, the bottles look completely normal. The water is still liquid. But slowly, the temperature starts dropping. Tiny ice crystals begin forming inside the bottles. Then those crystals grow. The water gets cloudy. The freezing line moves through the bottle. And eventually, the liquid disappears. After enough time, I open the freezer. And this is the first big reveal. All 5 bottles are frozen. Not partially frozen. Not slushy. Solid. I shake Bottle 1. Nothing moves. Bottle 2. Nothing. Bottle 3. Nothing. Bottle 4. Nothing. And Bottle 5. Also completely solid. So now the real experiment begins. I place all 5 bottles on the table. And I start with our control. Bottle 1 gets absolutely nothing. No salt. No water. No treatment. It will tell us what happens naturally while the other bottles are being tested. Now Bottle 2 gets a small sprinkle of salt. At first, nothing. The salt just sits there. Bottle 3 gets more. Still, nothing dramatic. Bottle 4 gets a heavy layer. And now Bottle 5 gets covered. Salt crystals spread across the frozen surface. For a few seconds, it looks like we've done nothing except make a frozen bottle salty. Then, look at Bottle 5. There. Something is changing. The surface is becoming wet. Tiny liquid patches are appearing underneath the salt. And now the question changes. It's no longer, will salt do anything? It clearly is. The question is, how far can it go? I leave the bottles sitting side by side. Bottle 1 remains dry and frozen. Bottle 2 has a few wet spots. Bottle 3 is developing more liquid around the salt. Bottle 4 has an obvious slushy layer. And Bottle 5 is changing the fastest. But here's the first twist. The outside is melting, while the inside is still frozen solid. That matters. Because salt isn't magically turning an entire frozen bottle into water. It works at the surface. When salt dissolves into the tiny amount of water on the ice, it creates salty water with a lower freezing point. That means some of the surrounding ice can melt instead of immediately refreezing. And the colder the ice is, the harder this process becomes. So now I want to push the experiment further. I add another layer of salt to Bottle 5. And this time, I spread it around the entire surface. Within moments, the bottle is surrounded by wet patches. Salt crystals begin disappearing into the liquid. The ice becomes rough, then slushy, then wet. But Bottle 1, still frozen, completely unchanged. This is where the difference between the bottles becomes obvious. Bottle 2 has a small reaction. Bottle 3 has a larger one. Bottle 4 has even more melting. But Bottle 5 is now surrounded by a noticeable layer of salty liquid. So I remove the bottles from the table and put them side by side again. And now they don't even look identical anymore. Bottle 1 looks like it just came out of the freezer. Bottle 2 has minor surface melting. Bottle 3 has obvious wet patches. Bottle 4 has a thick, slushy coating. And Bottle 5 looks like the salt has attacked the ice. But I don't want to judge the result from the outside. Because there's one thing we still don't know. What's happening inside? This is the part one was most curious about. So I take Bottle 1 first. I cut into the frozen section, and inside, it's still solid ice. Exactly what we expected. Now bottle 2. The outer layer is softer, but the center is still frozen. Bottle 3. Same story. More surface melting, but a frozen core remains. Bottle 4 has gone even further. There is noticeably more liquid around the outside, but underneath it, ice. And now it's time for bottle 5, the bottle that received the biggest salt treatment. I cut into it. And this is where the experiment gets interesting. The outside has changed dramatically, but the center is still frozen. The salt didn't destroy the frozen bottle. It attacked the ice from the outside inward. And that gives us our answer. But I'm not finished yet, because I want to know whether adding even more salt will eventually create a completely different result. So I take bottle 5 and give it one final treatment. More salt. A lot more. I completely cover the remaining exposed ice. Then I wait. The salt begins dissolving. The surface becomes wetter. More ice starts disappearing. The slush spreads. And now the bottle is sitting in a pool of extremely cold, salty water. This is the point where the experiment looks almost backwards. We're watching ice melt, while the ice and salt mixture becomes extremely cold. That's because the salt changes the freezing point of the water and the melting process absorbs heat. It's one of the reasons salt and ice can be used together for powerful cooling. But even now, the frozen core refuses to disappear instantly. And that is the biggest lesson from the entire experiment. More salt doesn't mean a completely frozen bottle suddenly becomes liquid. The salt needs contact with ice. It needs some water to dissolve into. And the temperature matters. The result is a battle between melting and freezing. So let's make the final comparison. 5 bottles started exactly the same. Bottle 1 received no salt. It remained almost completely frozen. Bottle 2 received a small amount. Some surface melting occurred. Bottle 3 received more. The reaction became stronger. Bottle 4 received a heavy treatment. The outer ice became significantly slushy. And bottle 5 received the maximum salt treatment. It showed the biggest transformation of all 5. But the final surprise is this. Even bottle 5 never completely surrendered. After all that freezing, all that salt, and all that melting, there was still ice inside. So did salt beat the frozen water bottle? Not completely. But it absolutely changed the battle. The salt couldn't instantly melt a bottle frozen solid. Instead, it attacked the surface, created salty liquid, lowered the freezing point, and slowly pulled the ice toward melting. And that's why the visual result was so dramatic. 5 bottles started frozen solid. 5 bottles faced the same conditions. But once salt entered the experiment, they started behaving completely differently. The control barely changed. The heavily salted bottle changed the most. And the biggest surprise wasn't that salt could melt ice. We already knew that. The surprise was how much ice could remain frozen underneath while the surface was already melting. So the winner of this experiment isn't really the bottle that melted. It's bottle 5. Because it proved that salt can dramatically change the surface of solid ice without immediately defeating the frozen core. But now I want to take this experiment one step further. Because if salt can attack frozen water from the outside, what happens when we combine salt, ice, and another extreme temperature test? That could produce a completely different result. And this time, we might finally find out what it takes to make a frozen bottle actually fail.